Today we're going to be talking about Wacker oxidation, and that's just a process that's used industrially to create a methyl ketone, which has a CH3 group and a carbon double bonded to an oxygen as its functional group from a terminal alkene, and that's an organic molecule that has the carbon double bond at the end. So let's look at an overview of the process since the reaction mechanism is quite long. So first, you start with your terminal alkene, shown here. You see that carbon double bond at the end, and the R group representing the rest of the molecule, and you get your methyl ketone. So this is your methyl, your R group, rest of the molecule, and your ketone is that carbon double bonded to the oxygen, that functional group. And in this reaction, you use PdCl2, palladium chloride, as your catalyst, and you use copper chloride, CuCl2, as your co-catalyst. And this just helps you regenerate this when you're at the end of the reaction. And these are the conditions that this is under. So DMF is a solvent that just makes everything a little bit more aqueous, and the main solvent is water. And this is the temperature it's at, and this is another condition. So the first step would be complex formation. And it's not shown here, but complex formation is basically taking PdCl2 and adding 2 more chloride molecules to it, so you get PdCl4, which is easy enough to understand. And then alkene coordination is a process of sharing electrons with the metal ion, in this case is palladium. So the pi electrons on the terminal alkene are used to basically connect to the palladium through the sharing of electrons. So you can see that here. And palladium is depicted as sitting basically in the middle of the double bond, but in actuality, since you know that a bond consists of sharing of 2 electrons, covalent bond, that means that really only one of these carbons are involved in the sharing of electrons. Yeah, so the pi bond is used as a coordinating electron pair. And then third step would be ligand exchange, which is not shown here, but that's basic. A ligand refers to an atom or a group connected to this metal atom, and exchange would be taking the chloride that used to be here and exchanging it for a water. So you can see here that there used to be Cl over there, and now it's an H2O. That's ligand exchange. Step 4 would be nucleophilic attack, and this specific step is not set in stone yet because it's not discovered yet whether the nucleophilic attack is from an outside water or from water within the molecule. But basically what happens is that the water molecule attacks the secondary carbon on the terminal alkene, and that results in the OH here being bonded to the secondary carbon and the water molecule being deprotonated. So you can see the H plus coming off of that. And then step 5 is the rate determining step basically, and that's also not shown here, but essentially one of the Cl's is kicked off of the molecule to reduce palladium's formal charge from 2 plus to simply just plus. And step 6 is the beta hydride elimination. So breaking that term down, beta refers to this atom right here. Alpha is the nearest adjacent molecule to the palladium, and beta is just the one that's most adjacent to the alpha. So here you have alpha, very close to the palladium, and beta, which is right off of the alpha. And hydride refers to the hydrogen off of that, and it's hydride, not hydrogen, because it takes both of the bonds, both of the electrons within the bond, so it has that -1 charge. And what happens is that this is eliminated, which means that this bond gets broken right here, and what happens is that the hydrogen bonds to the palladium, as you can see here, and the palladium kind of reassumes its position, sitting in the middle of that carbon-carbon double bond. Step 7 is a 1,2 insertion, which is a little bit hard to describe, but you can see it pretty easily. So essentially, this group right here is inserted between the palladium-hydrogen bond that used to be right here. And the way that occurs is that these two bonds, palladium-hydrogen, and between one of the bonds in the pi bond, in the carbon-carbon bond right there, are broken, and then these two bonds form. So you can see the palladium carbon bond right here, and the hydrogen to this group right here, the ethyl group, right there. So that's your 1,2 insertion. Step 8 is another beta hydride elimination, where you can see the same thing occurring basically. This alpha beta hydride right here breaks off of the beta atom, bond to the palladium, and then the bond right here, the electrons here go in the oxygen carbon bond, and you have that pi bond right there. Step 9 is reductive elimination. And what happens essentially is that you remove all of the ligands off of the palladium, and that reduces it to an oxidation state of 0. And when that is gone, then you have your desired product, your methyl ketone, since this is free. And you get HCl and H2O as your byproducts. And to make this process a little bit more efficient, you want to regenerate your catalyst. So remember we had PDCl2 as our catalyst. Now after you take off all the ligands, then you only have palladium. So to regenerate your catalyst, use CuCl2. You take the two chlorine atoms off of one of them, off of each one. You get PDCl2 and you regenerate your catalyst. That leaves you with 2 copper chloride, and you want to regenerate that back to the original co-catalyst. You would use an oxygen plus 2 HCl. You get your byproduct of water, and you regain your original co-catalyst. So just a comparison model to clear that all up would kind of, you can think of potatoes being fried in an air fryer to make french fries, right? So ethylene, which is your terminal alkene, is represented by raw potatoes, and your catalyst is your air fryer, PTCl2, and your desired product would be french fries, which is your ethanol. And that's the process in a nutshell, the most important parts anyway. And to regenerate your catalyst, remember after the reductive elimination, when you take off the ligands, you get palladium with an oxidation state of 0, and you want to regain its original state of PCl2. So you would have your dirty air fryer, right? And you want it to work better. So you would add some soap. You would regenerate its original state of being clean, or being PDCl2, and your soap would be your co-catalyst. And some applications is mainly it's used to make ethanol, and ethanol is used in the manufacturing of resin, disinfectants, perfumes, drugs, and other products, so it's pretty important in manufacturing. And Wacker oxidation can also be used to make more complex compounds like this one right here, and you can see that the mechanism you can see right here is the main one, is in the first step of this synthesis. And that's about it for Wacker oxidation. Thank you.